that'll help you. Okay. So Amira, welcome. And hello, Jane. I think I said hello to everybody else. So abstraction and modeling, Shema, is we're talking here about when we have a lot of information and we want to just filter out and just focus on the important information that we need for what we're actually going to do. We could call that abstraction. And modeling goes around along with it, because with modeling, we're either going to write something down or we're going to put it into a graphical model, which will represent the part of whatever it is we're interested in, but only the important parts. So we're leaving out unnecessary details. And we do that by focusing only on the parts that are important. So that's abstracting. Modeling, it's not exactly the same as abstracting, but it's kind of similar, right? Modeling, what we're going to do is we're going to have some representation of that, which sort of makes sense and has already excluded the unimportant parts. Now, the reason why abstraction here is in highlighted as opposed to the others is I hope you recognize those four things. Those four things are the components of computational thinking. And we've already spent in last week some time speaking about decomposition and pattern recognition. I hope you remember that. So decomposition, taking a complex problem and breaking it down into parts that are small enough, each of those individual parts which we can then solve. Then pattern recognition is where we notice something is repeating throughout our problem description or as we're doing our solution. And so that repeating pattern could, in a computer solution, could be perhaps approached with a module, a function. So there we are. Now, the reason why I'm doing it like this is because, as you know, I have some notes that come at the bottom of the lectures. Those notes I've been told I'm not allowed to give you, but so I'm not going to give them to you. But we can see them here, and you can look at them on the video, right? So, I mean, you know, you'll see some of these notes will come up from time to time. So I'm trying to give you the benefit of everything that's there. I probably should make this just a little bit smaller so it fits in the screen. So what is abstraction? So as it says there, suppressing means to, it's like if you put a blanket on something, that would be suppressing it, you know, that you couldn't see it and that it's covered, right? So we're covering up the things that are not relevant to us. So we're only focusing on the things, and the only things that we're making visible are the things that are important to us. And that's going to be an abstraction. We do that a lot in mathematics, you know, y is equal to 2x plus 1, right? That's an abstraction of a problem that you have. It's actually an example that we did in our first, was it lab or assignment? Do you remember that? Remember the diagrams with the blocks? That was, we could abstract that problem down to y is equal to 2x plus 1, and we did. And so that was a way of solving that. Oh, sorry. Now, when I looked at this first, I thought, oh yeah, that's periodic table. All right, so maybe some of you studied chemistry like I did. It kind of looks like that, but if you look at it a little bit closer, no, it's not about periodic table. It seems to be about some particular elements of computing problems and, you know, I guess how they fit together. So if you look, they're color coded. And so the things there in green are components that have to do with when we're doing algorithms. So our algorithms, we're going to have lines in them that represent the actions that we're going to do. We have one line after another. That's our sequences. Decisions, with the decision box, we've already done the flow chart once, right? And so you've seen a decision box and you've seen iteration. Maybe an iteration would be where an arrow in the flow chart comes back. All right. Now, the other way we do iteration in a pseudocode would be we'd do indenting and we'd have a while or a repeat until or something like that. And that would be able to show iteration. Iteration just means we repeat a particular bunch of code until some result that we want is obtained or until a particular time. Often we do it counted as well. Okay, so the green is about algorithms. The yellow is about abstraction. So in abstracting, we want to find out what are properties of things. Now, when I looked at this, actually, a lot of it has to do with if you were doing data analysis Data design, you would do that if you're going to be creating databases. And so you'd go through a lot of this process when I look at these notes. But yeah, you'd want to know, okay, so there's some there's some item that we want to gather some data about it. What kind of data do we want to gather? We're going to call those things properties. Maybe we want to gather data about people, right? So there's person. And so that person has a name. That would be a property. Then the type of the data we record. So I hope you're familiar now with the ideas that we can have data which is going to be of type numeric type. Numeric type could be divided into, we could have float type, which allows for decimal numbers, or we could have integer type, which is only whole numbers. So we got types there. Now, when we get to dictionaries, that's not going to happen with you guys in this year, I don't think. But when you do your second subject in Python, one of the things that you'll learn there is about using the various data structures that we have available to us in Python. In order to understand those, you would have to know a little bit more about object-oriented programming, because that's what it is. You know, you have an object which you create, you have this thing called a dictionary. The dictionary is where you're going to store your various data that you're going to need in your program. A list, we also sometimes refer to that as an array. So a list is going to be a bunch of data, usually of the same type of data, which is somehow related to each other and can be sort of ordered from first to last. All of those things you don't need to know now, but I believe before the end of this course, we'll have done lists, iterations, and sequence definitely. Yeah, we won't be going into object-oriented programming in this course, so you're lucky about that. All right, so that's coming next time though, in the next courses that you do. All right, so I hope that I've already made this point clear. With abstraction, we are focusing only on the things that are important to us, right? So we're actually removing from our model, removing from our idea of what it is we're working on, anything that is not sort of going to help us to do our solution. So we only consider the relevant information. Once we've only considered the relevant information, we have to have some way of organizing the information that we have, and we'll do that in a model. And from the model, we can build our solution. What's it say here? For example, a calendar is an abstraction of time. Yeah, it gives names of the day, week, year, and our observations about how long the Earth takes to complete certain movements. So, I mean, you wouldn't want to have to say to somebody, okay, when the Earth has completed another 2/365 sort of revolutions of the sun, and when the Earth has spun around twice, 2.5 times, I'll meet you at such and such a place. You don't want to say that. You want to say 2 days from now, I'll meet you at such and say halfway through the day. So we've abstracted that. What I was talking about, the Earth and the sun, that's what our calendar means, right? The calendar is about how long does it take the Earth to go around the sun, and how long does it take the Earth to spin on its axis. And so, but we don't need all that information to be able to talk to somebody about where we're going to meet them for a Starbucks, right? And so that's what we mean by that. All right, so the Rotherham Underground. So when they say underground, this is similar to the London Underground, I suppose, which is a much, much bigger network. And so the reason why they chose this one is this is a mythical, or yeah, it's not a true, right? So there is a little town called Rotherham, but it doesn't have an underground. I guess they just use buses or something. But if they did have an underground, then it might be like this. And so this on the left is some map that represents major parts of Rotherham. They're there. You can see roads. I think you can see different colors represent different types of uses of the land. So, I mean, there would be an industrial area, there'd be residential area, there'd be parks. You'd be able to tell by the different colors there, or sort of different shadings. And, that's all very interesting. And it's also to scale, so that if you hopped in your car here and drove over to there, you could, by looking at the map, you could sort of guess about how long that would take. And also, so there's other details in there. If we zoomed in, like you do on your Google Maps or Waze, you can probably see buildings and stuff like that. That's all very interesting. A lot of detail. But if you're riding in the train, in the underground, they call it, you wouldn't have a map like that on a wall. And the reason why is because most of that information you don't need while you're riding on the train, right? What do you need to know when you're riding on the train? Well, you need to know where you are now, which station did you leave, and what's the next station. That's about it, all you need to know. And you need to know, well, what other stations is that station connected to? As long as you know that, you're pretty good. And that's the kind of thing that you would see. So if you had a metro or underground that was like this, your metro diagram might look like that. And it doesn't actually, it's not in scale. You know, it doesn't represent a lot of the stuff that's in there is not shown. We can't see those industrial areas, those residential areas. We can't see any of that. All we can see is next station is there. And if I get to that next station, I can go to these other stations, which is all the information that you need if you're riding in an underground, right? So we have definitely done an abstraction there. And from our abstraction, we've got a nice little model. Here's is that Rotherham? No, this is Washington, D.C. Metro, sorry. That's interesting. And of course, some of you may have seen or may have ridden on the metro here in Doha. And so you'd be familiar with the idea that they put different lines, different colors, right? And so, you know, there's the Lusail line, that's one color, and there's another line that goes out to, where is that? New Rayan, where the Gulf, is it called Gulf Mall of Qatar? Is that what it's called? Yeah. So there's different lines that go, I suppose there's one that goes down to Wakra or something. Yeah. I've never been on there. Anybody else like me never been on it? Or you've all done it, right? My kids do it. Why am I going to go in there? I'll just ride my motorbike. All right. So yeah, anyways, the different colors give you an indication of different places that you might, well, I guess the red actually means that you have a rail car that goes here. So you could get on here and go to sleep and end up there. But in the middle, you could stop there and go to a different carriage and then end up somewhere else. And I think that's what kids do, actually. So cheap on the metro here, right? You just go and spend 2 hours riding around, right? And get off at this one, go to the mall, have a coffee, then go to the next one, right? Which is really cool, I suppose. And apparently they do that. So what is this? It's designed to help passengers. And therefore, it doesn't need a lot. I guess you do need to know where the river is, because you might be crossing the river and okay, I'm crossing the Potomac River. So I'm kind of coming downtown. Yeah. I have ridden that train system because I went to Washington and I stayed out on the northeast towards Baltimore, and I took the train in, and I couldn't figure out how to get on that train. Anyways, some helpful people helped me. Not far from Washington, D.C. Washington's here, right? Is this place. This is Virginia. And there's a map. And of course, you've seen those, right? Anyway, so when you're looking at a model, so a map is a model, what you'll consider, and if you wanted to make a model, what you would consider is, what are the users of this model? What do they need? And so, and who are the users? And so, for example, in this case, probably the users are going to be people who drive cars or trucks or something like that. And they kind of want to know. So that's why we have these shields with the numbers on them. The shield with the numbers telling them which highway you're on. That'd be good to know. And of course, every couple of kilometers as you drive down the road, you'll see a little sign that says you're on that road or not. And so that's good. And you know, you're going to have some other information there too. So yeah, the map is designed to meet the requirements of the user. So it's different than the Metro map, because Metro people, they don't have to, they just have to know where the stations are, right? So they need to know what line they're on, but they just, and they need to know where the station's on. And there we have it. So here's another map. Actually, this is Virginia as well, but you see the shape seems to be changed a bit, and this is a weather map. And yeah, okay. I'm not sure what we're supposed to get out of this, right? So it's the same map, but the point that I was trying to make a minute ago, different users have different needs. This is the user. Again, it might be people driving, or it might be just people going out. Maybe I'm going to do some gardening today or something, right? Is it going to be good for gardening? Well, I suppose 82 degrees would be all right for gardening. You know, that's in Fahrenheit, and 82 degrees would be like about 26. Bit warm for gardening, actually. All right, so what is abstraction? I hope we got that point. Maps are physical abstractions of physical things. So a physical thing is like the land, the city, the state, and you know, where are all the things there? Information abstraction comes from a physical abstraction. You do need to be careful with these words, because the way that we write the quiz questions and the test questions, yeah, they're going to be picky about that. I mean, you know, and they might have a question which will say something like, a map is A, physical abstraction of a physical thing. B, information abstraction. You get the idea? So you know, things that might be required in a map would be properties, types, yeah, whatever. Actually, this is not to do with a map. This is an information abstraction. And notice that it separates and makes a difference between a physical abstraction, which is we're looking at the world and we draw a map, and an information abstraction, where we're saying, okay, we got some information that we need to do something with. You know, maybe it's like the census of birth dates and all that kind of stuff. That's an information that we could abstract, and we'd have all the people, what are their names, how old are they, that type of thing. Types, I hope you're familiar with those. I've already mentioned integer and float in this lesson. There's another one called a string, and yeah. Okay, so a list or an array is also another type of data, but it's a complex type. And a string is actually a complex type of a simpler type than a string. I don't know if you're familiar with this idea, but we have this idea of a character. A character is a single part of something that makes up a string. All right, let's have a look at this. So I told you that we would get into the idea of data modeling. And just there in that previous slide, we looked at the difference between physical models and information models. So here we have an information model where we want to record, in this case, details about movies. And so there's a bunch of details that we want to have. So we know that this table is for the benefit of online customers. So that's why we refer to that as the stakeholder. The name here refers to the name of the table, because we have other things here, which are titles, which is the title of the movie. And so each of these things here would be properties of the entity. The entity would be the object that we talk about with our object-oriented thing. So in this case, in this table, a table is going to be made up of entities, and here refers to those as instances. And instance of the entity, which is each of those is a different row in the table. So each row in the table represents one particular movie, and that's why we're referring to it as a real world entity. Each instance is a real world entity. So Moneyball is a movie, and all of these things are characteristics of or properties of that object. And so each of those properties forms a column in the table, right? Or we refer to that as a field. So we have fields and we have rows. And the rows are the instances and the fields represent the properties. Hopefully that makes some sense. You'll do a bit more on data modeling in some data course that you'll do later, I suppose. All right, so I guess the idea here is we can abstract things down to a certain level, so abstract that we only have a few little bits of data in there. And, you know, we can abstract on different types. We can have different focus. And so we can overlay those over each other. Now, the idea is to get that as a right balance. We have to have the right amount of information in our models. Not too much, because then the model is hard to understand, but it must have enough so that all the important things can be gained from the model. And all right, so yeah, as it says, when you put more layers on the model, then more details are going to be suppressed, so the thing gets more simpler. So maybe we can see this in here. This represents two different ways of looking at an email. So on the left, we have abstracted it. On the left is more abstracted than on the right. On the left, we have abstracted the email into just the very basics of all you sort of need, and you would represent it differently. On the right, we're actually sort of showing how that abstraction represents things in the real world. So for example, on the right, when we go to write an email, we're going to have some user interface, and we're going to log in and, with a password. Once we do that, we're going to start typing or create our email. Our email will actually be a bunch of zeros and ones, lots of them, sort of joined together in characters and paragraphs and together, right? And so now those things, the zeros and ones, they could be represented in a model as being in the computer memory. So the computer memory just holds those zeros and ones. And then the email has to go from that computer where you are writing the email to the person who's going to receive the email's computer. That's going to happen on a network. And how that is going to be transmitted on the network is what we would call this a modulation of a computer voltage. And so what this graph represents is changing between 0 and 5 volts. So the idea being that 5 volts is a 1 and 0 volts is 0. So by doing that, we can represent all of our zeros and ones and pass them across a network. And so this is what it's like physically, and abstractly, we'd just say network. And I mean, especially if you're not a network person, somebody else is going to take care of that for you. But you need to know that what you need to know in this model is that we open an email application. We write our email, which is stored in computer memory. And then that email, which is in the memory, is transferred to a network so that our recipient can receive it. If you were the hardware technician, you would also know that there would be something like this happening. And so as it says, there are different layers of abstraction. Concept is computer readable. I hope that makes some sense. Right. Now, in this diagram, we have an abstraction that has now been represented by a model. And our model, we have a vehicle, and a vehicle has various properties. But the thing is, we have another object, which is our van, and the van has properties which is the same as any other vehicle. That's mentioned here, right? The van has all the properties of a vehicle, plus it has some own properties. So in other words, vans have some properties. If we had a rental company and we were storing information about all of our vehicles, when it came to vans, we would store some information that we didn't store about the other vehicles. So that's what it means here. All the vehicles, we restore their registration number, their mileage number, all of that kind of stuff, color, how much did it cost, all those. But with the vans, we store all of that, plus we store what is their storage capacity, because this is a rental company, I guess. And when somebody comes in to rent a van, maybe they want to move a lot of stuff, or maybe they want to move a little bit of stuff. So they'll decide on the storage capacity in the van, which van they're going to take. Now, in object-oriented programming, the point that it's trying to make here, and you can see that there, as I said, that'll show up on the video if you want to look at it later. But we have this concept of inheritance. Inheritance means that we can have, and hierarchy. Inheritance means that we can have child and parent objects. And so we would say that the van is a child of a vehicle, and it inherits all the properties of the vehicle. So does that make sense? So we can say that, and you can do that in your modeling of an object-oriented. Yeah, so I hope that makes sense. Whereas if we're just looking at the vehicle object, we don't necessarily have a record of the storage capacity. That's only in its child, the van. Okay, so I think I've sort of related to this a little bit already. You want to get a balance. You could be doing too much of abstracting, and so that you've suppressed too much information. And then then you get a situation where I want to record something about something, and I don't have the properties in my model to record that. So, I mean, in this one here with the vehicle and the van, I didn't do the van thing, right? I had all these vehicles, and then I come across this van. Oh my gosh, you know, I don't have anything about storage. What am I going to do? So I would have to either edit my model of the object, the vehicle, or else I'd create a new one, a child, which would be my van. And this we call, I think it's in this slide or the next one, we call that leaking. So where you are leaking details from something that we've suppressed. We didn't record in our model that the storage capacity was there, but we need it. And so what are we going to do? That little bit of data is leaking. And so that has to be taken into account. Breaking is not spelled by that, actually, like that. That's annoying to me. Yeah. So, yeah, maybe because I'm a petrol head, you know. Not everybody's a petrol head. But if you're doing a lot of braking, I suppose you want to record when the brake pads need to be replaced. And so maybe that has not been recorded in your model, and now you want to record it. That would be what we'd be calling leaking. And maybe you have to modify and change your model to make that to happen. So that's a leaking. And also in the previous one, I hope I made that clear. In the previous one where we had the vehicle and the van, if we, for any reason, we're just working with the vehicle and we wanted to know the storage capacity, we don't have it. So we got a problem. So we would have to create that new object. Modeling. So I used to make model airplanes when I was a kid, right? What I noticed about the little model airplanes is they look the same as the big airplanes, but they don't do the stuff that the big airplanes do, right? They only do the stuff that I wanted them to do. You know, I used to paint them, and then I'd hang them up and, you know, dogfights and stuff like that. That's what I was doing when I was like 11 years old or something. But the thing is, it's a model, right? It does everything that I needed it to do, but it wouldn't fly around or anything. And there's no little guy in it. You know, and so it was kind of simple. It's just made out of plastic. I hope that gives you an idea of what I mean, and it's true for other models. Typically, they represent something in the real world, but they're a lot simpler, and they only have the aspects in it that we need. So it could be a model airplane, or it could be a model of your data. So it represents a real world, but it excludes the details. Like the model airplane doesn't have working engines. You know what I mean? Things like that. There's a lot of stuff that's excluded because we didn't need it. We just needed it to look right in 3 dimensions. Yeah, so actually when they make cars, they do that too. They make full-size cars out of clay and they sculpt them, right? It's just clay. And then they put them in a wind tunnel and they take lots of photos of them. Doesn't have a motor, doesn't have anything, right? It's just to get the shape so that people will think that's really cool. And also maybe so they get some efficiency out of it. A lot of models. Right, so this diagram is trying to represent some relationships. So yeah, we got relationships between entities. So we have a model entity and we have some reality. And how is the model and the reality, how are they related to each other? Well, reality can be represented by a model, and a model is going to hide some details of the reality. So this kind of modeling you'll do when you do what we call entity relationship modeling. Entity relationship modeling will help you when you go to design databases. And that's what you do. You say, okay, so I have a bunch of information, you know, this information can be represented by different entities. This entity is related to that entity in this way. That one is related to that one in that way. A lot of the, so we have relationships. When you do database, and you will do database in your course, I believe everybody, you probably have to do at least one database course. You'll be talking about relational databases. In relational databases, we tend to represent the data in tables, and the tables have relationships between them. And so what are those relationships? Those relationships allow us to separate the data into different tables, each of the different table representing a different entity, each of the entity having different properties. The properties of each entity would become the fields of that table. And then, but each of those entities would be related to other entities. And how would they be related? Well, by these possible things, right? They could be that one entity belongs to another one. So this is the hierarchy, parent-child thing. And this is similar. C contains D. That's particularly for sort of repeating entity, information. E happens before F. G occupies the same space as H. Those are some things that could be modeled. I have to say those aren't the more common ones, but yeah, okay. Let's go to the next one. So entity relationship labels go with entity and relational database tables. I don't know why, if that rhyme was sort of thought about for that, but anyways. So we have properties, we have rules. Rules, we refer to those as our business rules. The business rules are how things relate to each other in the business. And so some of that's going to be recorded in a model, which is going to be a relationship database model. It might also be recorded in models like a data flow diagram or whatever. Classification of the entity. So an entity can be of different classifications. If we were modeling the computer system here at the college, we would model things like lecturers, we would model students, we would model administrators. Each of those would be of a similar type. Then we would model our assets, like our computers in our rooms. Those would be of a different type. And so we have different types of classifications of them, right? So we have our hard assets, and we have our human resource, and we have our customer base, which is our students. And so each of those is a different sort of type classification of that entity. Rules, how are those things related? If you really wanted to get into it, right? So here we are, we're in this class. You could have a table which represents this class. In this class, we would have the name of all the students and their student number, and they would have my name. So there would be a table somewhere which represents all of the lecturers, right? And then each lecturer has a unique identifier, you know, their key. And then each student would have a unique identifier. We got a lot of data about the students, you know, and so we'd have a table about the students, a table about the lecturers. We've got a table about all the classrooms. And so when we have a class, those three things have to come together. So we have a relationship, right? Lecturer teaches class in this room at this time. Student comes to class in this room at this time. Lecturer and student, lecturer, student, student is lectured by lecturer. All of that thing is captured by those three tables and the relationships between them. Does that make sense? And so we don't have one big table which just says, here's all the lecturers and students and classes in the college. That would just be a big mess, wouldn't work. We have a table for all the lecturers, have a table for all the students, and we have a table for all the classes. And at some point, they have relationships between them, you know, when we come together in a class. Does that make sense? And I need to be careful with that word class, because it's actually a special word when we talk about object-oriented languages. I'm talking about the class that you've been talking about since you're in grade 1, right? I mean, this room, right? So as opposed to a object-oriented class, which we're not talking about. All right, so static versus dynamic models. Static just means things don't change. And it is quite possible that you could have a bunch of data or a system on things that don't change, especially historical things. You know, if I had a database about the rulers of Qatar between the year, I don't know, 1901 and the year 2015, that's not going to change, right? Now, it'll change from 2022, but, you know, in there, all that stuff's going to be the same. There'd be a lot of relationships that would be interesting, a lot of things that they did, but none of that's going to change. That's a nice static system, as opposed to a dynamic model where things do change. And so we have transactions, things are happening all the time. Any sort of real-time accounting system here at the college, our attendance system that I talked about at the start of the class, that's a dynamic system, right? When I finish this lesson, I will go there and I'll have to record people that are not attending. And that's going to be different today than it will be tomorrow or than it was yesterday. So those things are changing. We have transitions, we have transactions that are recorded by that. So we got a nice little model that sort of represents that here. The idea of this is we're still talking about the metro. You go to the metro, you have a toll. I have to admit, I haven't been to the metro here, but you know, I have been to metros and I have come across turnstiles like this. Where else do you see turnstiles like that? Yeah. Some stores had them, right? Anyway, so you come to the turnstile and you push and it won't let you move, right? So this is where you start, by the way. So the start point, the solid black start, we're starting here. We start from here and we push on the turnstile. You know, the turnstile's got these little arms that come out and they, you know, and you go in them and you go to the other side. It's locked, but then you're going, so this is something where we are in a locked state. Our pushing has no effect, right? We're pushing, but nothing happens. Then we put a coin in. And when we put a coin in the turnstile, actually nowadays, you'd probably just put your card on it or something, right? Your card, you'd have a special card and you'd put that on there, put the card on, and then the turnstile opens. And then when you push, you know, you're going to go through it and it'll be locked again. So yeah. Did I miss anything there? Inserting a coin is an event. So there's an event. It triggers a transition. So the transition is between the locked and the open state. So before we inserted the coin, there's no transition, nothing happening. It just stays locked. When we inserted the coin, we got our transition, pushing the unlocked turnstile. So when we push that, it's going to go back to locked. So it changes. Here's another transition. So we got two transitions, one when we insert a coin and one when we push an open or unlocked turnstile. Oh, what about this guy? Another German dude, right? Prussian is German. Leonard Euler, Prussian mathematician. Okay, so here's his problem is he's got this town, small town on the Baltic coast, right, between Poland and Lithuania or whatever. So it was called Königsberg. And it's a small town, but the thing is, it's got water in the form of a river and other things, which means that the different parts of the town are separated from other parts of the town by the water. So we have islands. And so he was supposed to come up with the most efficient way of visiting each one of these different parts of the town. And so this is a very similar problem to the traveling salesman problem, which was mentioned in one of the earlier lectures. Remember, I mentioned the traveling salesman problem? Traveling salesman had to go to a bunch of different cities, and he wanted to go to them and spend as much time, I guess, and as least amount of gasoline and time on the road, right? And so that would be the traveling salesman problem, which is similar to this. So actually, this one here is a little bit more limited than that, because he's supposed to make a way of going to visiting all of these places without ever going back over the same place twice. So I don't know, you look at it, I found it kind of hard, right? So, you know, you can go from one to one, you know, how do you do it without getting to one of the, going over the same place twice? And I hope that you see, I'm not asking you to sort of solve that, but I'm just asking you to look at it and see, can you see that it would be easier to solve that problem looking at this model than it would be to solve that problem looking at a map of Königsberg? Does that make sense? So what we have here is a model of Königsberg, which is a lot simpler. We've abstracted it down to something so simple that, you know, even an old guy like me maybe could look at that and say, yeah, I can probably, with a little bit of time, I can find a way of getting to each one of those parts of the island without going over the same bridge twice or the same, you know, road twice or whatever. If I had just doing it here, you know, got so many things that are confusing you that you don't need. Okay, there's a lot of words there. So with the graph model, so I guess Euler made the graph, and that was his way of solving the problem. And he came up with some rules. And as I said, it's a lot easier to do it that way. Another model. So this model represents the Earth, And just kind of like my model plane thing, you know, yeah, I don't know if any of you ever did that when you were kids, but making model planes, the challenge is to make it as realistic as possible, right? I mean, all you got's these little brushes with oil paints, but you want to make it as realistic as possible. And you got this little bit of plastic that you're painting stuff on. It's quite a challenge, right? We do want to do that. I've got something that is really simple, represents something that's a lot more complicated, but I still want to get as realistic as I can. So what these scientists are doing is they know about the Earth and they want to make a model which they can use that sort of, so the model here is a climate model. I mean, so based on data that they've got for the last hundreds of years, when it's been recorded, and they can actually go for thousands of years, and you might say, there wasn't any scientists 10,000 years ago, so they don't have any data from 10,000 years. Well, yeah, actually what they do is they go to Antarctica and to mountaintops and to Arctic, and they drill into the ice in Greenland, and they drill into the ice and they pull up the ice core, and the ice core, then they test it. And the oxygen in the atmosphere has two different isotopes. There's an O218, and there's an O216. And the O2, the relationship between the different proportion of O18 and O16 changes with the temperature. And when it's trapped in ice, then it doesn't change anymore. So you can go back thousands of years, hundreds of thousands of years, perhaps millions of years, if you can find ice that's that old. And then from that, you can say, okay, well, at that time, the average temperature, blah, blah. Anyways, that's what they think. Actually, yeah, never mind. You can use that particular method for lots of other things as well, but you can use it for that. So they're making a model, and the model is something that's simple, that represents the real world. And from it, it's a complex model, you might say, but yeah, it's complex, but it's simple compared to the real world. The real world is even more complex than the model, but they're doing the best they can. And as they add more information, they get a better model. They actually update the model as they go. And then all of us get worried because we notice that the climate's changing. What to do now? Okay, so this is a model. And this kind of model, we have this idea of cardinality, which is what is the relationship in numbers between any entity and its properties. And so we have a student, and we notice that each student has one date of birth, right? You're only born on one day. You can't be born on more than one day. Every student has each of their names. They only have one. They have one first name, then they have another name, right? They might have a couple more. Each student lives in one street, has one house number, in one town, in one postcode, but each student might have 3 phone numbers. Could be, I suppose. And so how do we model that? If we were going to do this, we could make a table called student, and we could put all those things in it, but we'd have to make another table because you have to have a cardinality of 1 to 1 in order to make a table for an entity. So we'd have to have another table, which would be our student to our phone number. That's just a little bit of data modeling fun that you guys will come across later. I don't know why we're doing all the data modeling in this course, but hey, why not? So another model. Problem is I can't read that. I don't know if you guys can. All right, so this represents a transaction, payment and delivery. And so we've got sort of things happening in order. What I hope you can see is by the way the arrow goes there, this happens before that happens, I guess. And then when this happens, then there's some relationship with this, and there's some relationship with the customer, and we get then they ship it, and then eventually we get it. Yeah, I mean, you could draw arrows on that, which would make it make more sense. There's a model representing a transaction or interaction. That's kind of it for this lecture. How'd we do? We started at 10, right? We're still recording. Let's stop there. And